Okay, so a worked example for you then on circular motion, although it's only this last bit that's actually circular motion, but that's okay. So we have 150 gram mass. I highlighted 150 grams because that's important. Is attached to one end of a light inextensible string. That means it's not going to stretch. And the other end of the string is fixed at a point P, as shown in the diagram above. The mass is held at point A, so that the string is taut and horizontal. The mass is released so that it moves freely along a circular arc of 250 millimeter radius. So that's also important. When the string moves through the vertical position, the mass is at point B, neglecting the effective air resistance, so there are no losses then. Calculate the energy, kinetic energy of the mass. So I have the mass, I have the radius, and I want to know the KE here. So I'm thinking by conservation of energy then, the KE at the bottom will be equal to the GPE at the top. So it's annoying. So that's the physics behind it. All I've got to do then is to stick the numbers in. And I've got, excuse me, mass 0.150, G 9.8, and the change in height between here and here, 0.25 meters, which gives me 0.37 joules. Then the velocity of the mass, well, that's an energy question as well. That's a half mv squared, of course. So if I do that, I get half mv squared is 0.3675. Notice I didn't use 0.37. I used my raw 0.3675 from the previous answer, which gives me 2.2 to 2 sig figs. You might say, well, why only 2? Well, I've got 3 here and 3 here, but G is only to 2, so I can only really give this answer to 2. Then the centripetal force, well, here's the bit that involves the circular motion that we've been doing. So we're going to say that the centripetal force is given to us by F equals mv squared over r. So we're going to stick in our numbers to that, which is 0.150 and 4.9 is v squared, what we got up here, divided by 0.25, which gives us 2.9 to 2 sig figs. And then finally, I can find it. I'm missing the last part of this question, irritatingly. The last part is the tension in this string, which should be D. Let's take the underlining off that. So the tension in the string, well, if we go back up and look at our diagram, it's the tension at this point that we're after. I should say tension at point B. I don't know why that bit of the question is missing. So at this point, we've got mg down, we've got T up, and we have the value of the centripetal force. So we know that the tension in the string will come to us via F, the centripetal force, is T minus mg, because T is up, mg is down, and F is the resultant in the upward direction here, as we know from our theory of circular motion. So we have, rearranging the equation, we have T is F plus mg. And if we do that, we get 4.4 newtons. Never forget your units. So there you have a worked example on circular motion.